Thank you for the introduction, and thank you all for staying until the last talk. I don't like giving computer presentation talks, so I said that I would do board talk, and there's no blackboard, but I'll try my best. I'll try to write big. So these skein algebras is in some sense, it's a quantum object. And instead of starting with the skein algebra, I'll start with the classical side and then go to skein algebra. So classical story, meaning non-quantum story. So I need a surface, topological surface. So I'll call it sigma, an oriented smooth surface. So for example, you would imagine something like this with some genus. But the difference between this talk and the previous talk is that I will almost never deal with closed manifolds. So for my talk, I don't really allow closed manifolds, but I rather almost always work with certain either non-compact manifold or manifold with boundary. So today I will either work with something like this, so closed surface with punctures, and sometimes I might call them punctured surfaces. So in fact, for today's talk, I can just work with punctured surface, but in the more general story that's relevant to the topics that I'll be talking about today, the more general kind of surface looks like there is a boundary, there could be a boundary, and some punctures, and also punctures on the boundary, so that the boundary components are intervals. But I think we can focus on the puncture surface. Anyways, you need a surface. And then the basic sort of object that I'd like to start with is this. So let me call it R sigma. It's what people call character variety, or SL2 character variety. It's defined as the space of all group homomorphisms from the fundamental group going to SL2C. So you collect all the group homomorphisms from the fundamental group going to 2 by 2 matrices of determinant 1, and you call two such things to be same if they're related by overall conjugation. So this is like two-dimensional representations of this group, but you're restricting to determinant 1 condition. And collection of all this thing is studied quite extensively. And to be more precise, this is sort of in the realm of algebraic geometry, because I'd like to see SL2C as a affine variety. So it has these 4 local coordinates. And in the case when sigma is a punctured surface, then you can easily see from algebraic topology class that this is a free group on some number of generators. So in fact, the collection of all group homomorphisms, to describe that is just, you can describe where each generator should go. So this part is just a bunch of product of SL2C as a manifold, or as variety. So kind of simple looking space, and then there's a conjugation action of SL2, simultaneous conjugation, and you're quotienting by this action. And usually if you quotient out by group action, things might be not very good. So in fact, I have to take, it's called the GIT quotient. That's what I'm doing. And what is really relevant here is what are the nice functions? Well, in the algebraic geometry language, what are the regular functions? So I can write something like this. So regular functions. And by this symbol, you can understand what's going on as something like this. So you just first take this easier part, which is just a bunch of SL2, and take the regular algebra regular functions, meaning all the functions that look like polynomial in these coordinates. So it's easy to describe. And then out of all such functions, you take the functions that are invariant under the action of SL2. So this, you can take this as a definition of, so that's, I'm describing what is the algebra of regular functions on this space that I'm trying to define. And you take the spec, so that R sigma, whatever that is an algebraic geometric object space whose algebra of regular functions is this. So, as I said, this was studied for quite a long time by many people. And so you can ask how to describe this ring. And then there's a most natural kind of functions that you can create as follows. So what you do, well, before going that, let me give a name. So this is, as I said, usually called the character variety. Or more precisely, in this case, SL2C character variety of the surface, because you can actually do the same thing with any algebraic group. But today I'll only work with SL2, so character variety, and I'm going to tell you some elements of the algebra regular functions. What you can do is you take any loop, so choose any loop, say gamma in the surface. And you can view it as an element of the fundamental group. So this is fixed, and then I'm going to create a function out of this loop. Function. I'll write it as TR gamma and call it trace function. Trace function. On this character variety. And what it does is that it eats a equivalence class of representation, or the group homomorphism. So it eats this rho, which is a group homomorphism. And what's the number it spits out is that you first feed in your fixed element gamma, then this is an SL2C element, and you take the trace. So you get a number, and then you see that this is invariant under the conjugation, and it's also easy to see that this is a regular function. So this TR gamma is an example of an element here. It's most natural element you can think of, and you can do that for whenever you have a loop. And then the classical result is that actually these trace functions generate the whole algebra of regular functions of this character variety. This is a result by Processi from 70s. Well, he proved more general theorem, but in this case it says that theorem Processi 76 is that this algebra of regular functions is generated by these trace functions, but you have to take all possible loops, like for all loops. So it's a huge generating set, but anyways, if you know everything about these trace functions, then you do have some control over this ring of algebra regular functions. And then what I'm not going to say that much is that this space also has a Poisson structure. You might want to say some degenerate version of symplectic structure coming from Goldman. So you don't have to know precisely what this means. This space contains, it possesses a Poisson structure. And in terms of the algebra, it says that there exists some Lie bracket, special Lie bracket, which is a binary operation on the ring of functions that satisfy Leibniz rule. And so this can be viewed as a Poisson variety, if you say, something like Poisson manifold. And in that case, you can think about the notion of quantizing that space. And so that's what we will do right now. And I won't give a precise definition of what I mean by quantization. I'll just be kind of vague and then just give an answer. This is the quantization. This is a quantization of this space or its ring of functions. So while I'm erasing, I can say certain things. So everything will be described in terms of algebras or algebras of functions. So we had an algebra, which is a commutative algebra. This you can add or multiply, but that multiplication is commutative because it's defined as the pointwise multiplication, so it's commutative. It's commutative algebra together with some extra structure, which I called the Poisson structure. So you have two different structures. And quantization means that, at least the algebraic part of the quantization means that you want to deform this data into a single non-commutative algebra that contains both this information and the Poisson information. So I'm going to be giving you that non-commutative algebra that deforms the algebra of regular function here. And that's what's called the skein algebra. And although we started from purely two-dimensional story, the quantum algebra will involve 3 dimensions, 3D topology. So let's go to quantum. Still about this surface, but now I need some 3-manifold, and that 3-manifold is what is called a thickened surface. So you take the product of your surface with some interval, let's say any interval you like, but I'll just choose this. So now you can think of like living in this atmosphere of Earth. Now you have an elevation, you have a height. Or thickness, if you like. And then we'll be considering things living in that thickened surface. What we will consider is that instead of loops living in the surface, we will talk about loops living in this thickened surface, or more precisely, framed links. Framed links living in this thickened surface. So link means bunch of circles embedded in this thickened surface. And framed means that, let me draw a picture. So when I draw a picture, I still kind of draw only surface because it's hard to, I don't know how to draw surface times interval in an efficient way. So whenever I draw a link living in this thickened surface, I almost always project it down to the surface and draw some picture like that. or maybe like this. But you have to imagine that this picture is living inside the surface times interval, certain thickness. And so this part means that, well, still there's no self-intersection. But when you project it down, there can be some self-intersection. So this part is the higher part, and this broken part is the lower. So that's what people call crossing. So you can use the projected diagram to represent these links living in this three-manifold. That's what they usually do in knot theory. And framing means that every point you choose a tangent vector in the ambient three-manifold, which is never tangent to the link itself. So it's like having a ribbon instead of just a link. And when I draw a picture, I don't draw framing because, so I consider these things up to isotopy, meaning homotopy, but within the class of framed links. So you can continuously wiggle around, and the usual convention is that you isotope all the framing so that it points upward, and then you project it down to a surface. So, for example, this diagram will be different from that. So I'm using the blackboard framing when drawing pictures like this, meaning that the framing is pointing toward your eyes. Blackboard framing. So that's a basic object that I will use. Framed links living in thickened surface. And then using them, I will define an algebra. So the thing that I'm erasing right now, you can think that for each loop, there was an element of this classical algebra. Now, for each framed link, there will be an element of this quantum algebra. So here's a definition. From 80s. Out of many possible versions of what people call skein algebra, this is the thing that's called the Kauffman bracket skein algebra. But today I will only talk about this skein algebra, so I can just omit saying Kauffman bracket and just say skein algebra. So it's an algebra where there is a certain parameter. It's traditionally, people use A, associated to a surface. So I'm going to give you a vector space structure and then multiplication structure. But more precisely, it's a module over a coefficient ring. And as a coefficient ring, today I will take ZQQ inverse or ZAA inverse. So this is the coefficient ring. Laurent polynomial in A with integer coefficients. You take the free module over this coefficient ring with basis being set of all isotopy classes of framed links. Isotopy classes of framed links in this thickened surface. So up to now, which means that your element is a linear combination of those pictures. Finite linear combination where the coefficients live in that ring of Laurent polynomials in integer coefficients. And you mod out by certain relations called skein relations, which I will write down right now. Modulo here's a relation that if you have this kind of picture, equals A plus A inverse. So that's called a skein relation. And what does it mean? It's giving a relation among three framed lengths which look almost the same except at a very small ball where they differ by these three pictures. So only locally they differ, and if they differ exactly as these three pictures, then they should be related by this relation, which is called a skein relation. And additional relation, which is very much related to the first one. It's somewhat mysterious looking, that if you have two framed lengths that's exactly the same except at a very small ball, where one has this unknot component and the other is nothing there, then they should be related by that. So for some reason you define the module this way. So that's the end of the definition for as a vector space, as a module. And then I'm going to give you the multiplication rule. How do you multiply two such things? Perhaps I can write here. It is enough to tell you how to multiply two such pictures, because all elements are linear combination of these pictures. And multiplication is given by superposition of two pictures. You stack one on top of the other. So multiplication is by superposition. Namely, if you have two framed lengths living in the thickened surface, how do you multiply the two? K1 times K2. This is what I have to define. And what you do is, so everything is defined up to isotopy, so you can continuously deform within the category of framed lengths. Like, so you can't go over crossings. And the first one you isotope so that it sort of lives high. So you can just push up. And then take the second one separately and push it down. Well, you isotope your first one to some framed length that lives high up. And you do the same thing for the second one, but you isotope it down so that it lives in the lower part. And then you take the union. So this is the definition. So you're kind of putting K1 on top of K2. So that's the definition. So this is the definition of skein algebra. And you might think that if you have seen this for the first time, you might think that this multiplication is kind of stupid. But it is quite non-trivial, and in particular, this is, in general, a non-commutative product. Let me give you a picture example of this multiplication in the case of one-puncture torus. So let's say your surface looks like this, torus with one puncture. And then I'm going to try to multiply two framed lengths. So let's take this framed length. By that I mean the framing is taken to be upward vertical. So in this picture, you can imagine the framing to be outward always. And then you take this other framed length and try to multiply. Then what you do is, now you're going to put them together, but put the first one on top. So that's my definition. And already this is a perfectly fine element of the skein algebra, But if you want, you can use the skein relation to resolve the crossing and express it in a different way. So you just apply that skein relation here. That means it gives you, it lets you, no, the other way, express the same element as some linear combination of the other, A inverse. With no crossing, if you want. And then if you try to multiply these same elements, but in a different order, and see what happens, I'm going to leave it as an exercise, then you'll figure out that it's the same thing, but A inverse and A is reversed. So usually they're different. So usually they're not equal, unless A is 1 or minus 1. This algebra is, in general, non-commutative. In general. And so why do you consider such a non-commutative algebra? Is because this non-commutative algebra quantizes the character variety that we have seen before in a certain sense that I will not define very precisely what I mean by quantizing, but that's the meaning. So here's one meaning of why would someone consider such an algebra. So meaning one is that this skein algebra, as we defined, in fact, it makes sense also for closed surfaces too, up to now. It quantizes the SL2 character variety. In particular, it means that when the quantum parameter goes to a certain value, in this case 1 or minus 1, you get a commutative algebra, and that commutative algebra exactly recovers the algebra regular functions on the SL2C character variety that we have seen before. So in this case, more natural is when A goes to minus 1 for some reason. So this sort of recovers the algebra of regular functions that we have seen before, like isomorphic, as A goes to minus 1. So you just put A equals minus 1, then the algebra is isomorphic to that same algebra as before. Where if you have a framed link, then what is a corresponding function on the algebra regular functions on the character variety? You forget the framing, project it down to the surface, then you get a loop. So you can take the trace function, but in this case you have to take the minus of that. So it is a non-commutative deformation of the commutative algebra before, and also it contains, this non-commutativity also contains the Poisson structure that I just set the name of in a certain way. So you take the commutator, which is K1, K2 minus K2, K1, which is usually non-zero, and take this kind of limit. Then this recovers Goldman's Poisson bracket. So in some sense, this skein algebra is a quantization of the character variety that we have seen before. And this is all discovered in late 80s and early 90s. But I can also say one more meaning of this skein algebra defined this way, which you will like if you have some familiarity with 3D topology or knot invariance, that two, this skein algebra or its elements can be viewed as a generalization of knot invariance, like Jones polynomial. So it can be viewed as a generalization of very precisely saying Kauffman bracket polynomial, Kauffman bracket invariant, which is essentially Jones polynomial, which is a not invariant. Kauffman bracket invariant of knots, or maybe framed knots in S3. And this is the case when, if you take our surface to be R2, then the story recovers the Kauffman bracket polynomial, and we are, in general, dealing with more complicated surfaces than R2. So that's the definition and meaning, like basic meaning of the skein algebra. So anyways, you now have an algebra at your hand, and people wanted to study this algebra. So as an algebra, what do you want to study? You want to study some algebraic structures of this.
Part one, what's the meaning of the arrow? Does it preserve any structure other than possible structure or the addition or multiplication? So what do you mean by this arrow? Is it just separating that? Or?
I mean that when you put a equals -1, it's just isomorphic as algebras. Yes, and this is also, I can just, yeah, this element, yeah, this has to be put in quotation mark in some sense. Yeah, the second statement may be a little bit careful, I have to be, but let me not go into the details. Does that answer your question? Okay. So what do you want to study in general if you have an algebra? So the first, so you want to study various properties of it as an algebra. And I think one of the most basic property that you might ask is, how do you present it as generators and relations? And people like to have finite presentation in general. Meaning, can you find finite generating set of this algebra? And the finite complete set of relations being finite. So people usually want to do this for an algebra. And this is still much open, like nothing much is known how to present skein algebra in a finite presentation. So still much open. So if you are interested, you can try yourself. So that's not what I'm going to do today. I will. So what other thing you can do is that, so what is an algebra? Algebra is like a vector space with multiplication. And if you just sort of focus on the vector space structure, the module structure, I can ask whether there's a good basis, vector space spaces. And that's the thing that I would like to address. So a vector space basis. Or, well, in this case, I'm not actually defining it as vector space. I'm actually defining it as a free module, or module. So perhaps basis over this coefficient ring. That's to be more precise. And I don't know how canonical this kind of approach is, but at least if you have a vector space basis that is constructive enough, then you can use it to prove other properties. So at least it's very useful. Even if you don't see how fundamental this problem is, if you have such a thing, it will be very useful in proofs. And that was actually the case for the literature. And we can actually already observe how to find a spanning set, natural spanning set, using the discussion that we have had so far. So note that if you have any frame link, any element of the skein algebra, what you can do is, as we did in this example that we did for one-punctured torus, you can use skein relations to remove all the crossings. So you can resolve all crossings and also all unknots, which were these circles with the framing and nothing inside. So any framed link can be expressed as linear combination of diagrams without crossing or unknots. So at least that's a spanning set. So let me write that down. Is crossingless framed link diagram. Links with no crossings or unknots. Well, everything up to isotopy. Maybe I should say link diagram or framed links. I'm being a little bit sloppy. And we can easily see that that actually spans the skein algebra. Spans. That's kind of easy to see. So in pictures, such elements look like the following. It's a bunch of simple closed curves or simple loops, like that don't intersect with each other. But sometimes you can have many copies of the same component. That's also allowed. So you might want to call it multi-curve. Some people call it, or maybe essential multi-curve. I do allow small loops around punctures. So we just figured out that they actually span. Less trivial is that they actually form a basis. So they're linearly independent. I don't know what's the easiest way to prove that they are linearly independent, but it is a fact. It's a fact that it's actually a basis. And let me give it a name that people usually call it Bangles basis. For some reason that we will see a little bit of in a few minutes. So there is a basis, and indeed this basis was used in proofs of certain properties of skein algebras. So you might be content with this Bangles basis, but let me give you some more bases that's not exactly Bangles basis, but look a little bit different. So, but there are other bases too. And why consider other bases? Because some other bases have nicer properties than Bangles bases. Nicer. So we'll see what I mean by that. And to describe these other bases, I'm going to give you two other bases. And to describe them, I will first give you a little bit of different description of the Bangles basis, and then try to generalize from that. That is to say, if you have a multi-curve, sometimes you have multiple copies of a single loop that appears in a parallel manner, and I'm just going to combine them and just put the number of the components. And I'm going to call that kind of data integral lamination. So integral lamination is, so I'm not going to define it in words, I'm just going to give you a picture. So if I just take that picture, then I do the same thing, but I don't repeat the same loop, but just put number. So something like this. So now the data looks like, so integral lamination L looks something like you have a loop, simple loop, and integer weight, or positive integer weight, and you have a bunch of them, finitely many of them. And the condition is that none of these constituent loop gammas are isotopic to each other. So I removed all the redundancy. So lambda k, non-isotopic to each other. And none of them are contractible. Non-contractible. So no or not. So this thing I'll call integral lamination. So it's just the same thing as multi-curve, but written in a different way. And I'm going to call the set of all integral laminations as lam sigma. Integral laminations. And everything is up to isotopy. And so now let me give you a construction of 3 different bases of skein algebra. And it's easier to start with the case when the parameter A is 1. So I'm just going to give you bases, 3 different bases of the skein algebra. And I'll cheat a little bit and just put A is 1. So commutative case. And then I will tell you how to do the quantum case. For each integral lamination, I'm going to give you an element. And if you have a loop gamma with integer weights m, this is integer, I'm going to tell you how to turn this picture into 3 different pictures. One is just the bangles that so one way is just replace them by m copies of gamma, m parallel copies. So that's what we have seen before already. And I'll call it bang m of gamma. This picture is called a bangle. Other thing you can do is, so this is a case when m is 4. Let me not mess up. So instead of m disconnected thing, you can do m winding around. And that's called a bracelet. So brac. This is called a bracelet. And this is also a perfectly fine element of the skein algebra. There's no ambiguity of the overcrossing and undercrossing because I'm doing the A equals 1 case. So this is the m times winding around. And the third one looks like there's a normalization and sum over all permutations. So SM is the permutation of m letters. And what you do is you put the permutation braid. So these are permutations. And for example, when m is 4, this will look like, so all possible ways of connecting up and down. There will be many, well, so you do sum of all that and then normalize. And that's called bands. So band, this is a band. So I gave 3 different pictures: bangle, bracelet, band. And so given a integral lamination, you do this for every component and just take the product. or union, if you like. And that gives you one element of the skein algebra at A is 1. So for example, bang of an integral lamination, L. I do this thing, the first construction to all the constituent. So bang I of gamma I. So this is a product taken inside the skein algebra at 1. And you do the same thing for bracelet and band. And then you collect all of them, and that becomes a basis. So I'm going to call them curly B bang of your surface to be all these elements, bangle elements, where L lives in integral lamination. This is what we have already seen before, the bangle spaces. And you do likewise for the other two constructions, for bracelets and band. So you have 3 different sets. And proposition is that each of these 3 is a basis. So each is a basis of skein algebra at 1. So I already told you that the first one does form a basis. But how do you prove that the second one and third one also forms a basis? You can do it, you can try to prove it yourself, but let me tell you how to do it. Once you know that the bangle spaces is a basis, how do you prove that the other 2 is also a basis? So note that the bangle construction for a single loop component, which we have seen in that picture, is actually, you can view it as gamma to the m using product of the skein algebra. So you're actually putting gamma into a very simple polynomial, a one-term polynomial. And you can actually express the other 2 by putting gamma into some other polynomials, which are Chebyshev polynomials. So let me define Chebyshev polynomials. I'm going to give you 2 kinds. One is T and one is S. So these are one variable polynomial. The first one is called the Chebyshev polynomial of first kind. The second is called the second kind. And they're defined as the following. Recursive relations. So T0 is 1. T1 is identity function. And then the recursive relation is that the next one is x times the previous one minus. So that's the defining recursive relation. And you can go on. And second is almost the same. In fact, this should be 2. It's actually the key difference. So this is the only difference. The others, same defining relations. And these polynomials were known for a very long time. And you can compute, for example, like T2 will be x squared minus 2, whereas S2 will be x squared minus 1. And then the statement that you can prove by hand is that these 2 are actually results of putting gamma into these polynomials. if you are bored, you can try to prove that. So lemma is that bracelet that was the m times winding around is just putting gamma into the Chebyshev polynomial of first kind, and band is putting gamma into the Chebyshev polynomial of second kind. And you can easily see from the defining recursive relation that these are monic polynomials in degree m, and that's why you can easily prove by using this lemma that they also form a basis. So this was for skein algebra at 1. So what to do for quantum case? Because then now there's an ambiguity of the crossing, which one is overcrossing and undercrossing. For the quantum case, what you do is I will just use these polynomials. So I'm just going to tell you a little bit because I don't have much time. So again, we'll be enumerated by integral laminations. So for each such L, I will give you one basis vector. Let's do the bracelet, for example. Then L looks like these bunch of constituent curves with integer weights. And for each such thing, what do? You just take the k gamma I, where k gamma I is just gamma I lifted, so lift of gamma I, which is a loop in a surface, but you have to lift it in a link living in the thickened surface, but you just lift it at the constant elevation. Constant elevation with the constant upward vertical framing. That's what I call k gamma I. So that's an element in the skein algebra. You just put it in the polynomial. And you just take the product. So brach L will be just take the product. And the product order doesn't matter because each factor for different I, they commute. So you have 3 sets, and they still form a basis for the quantum algebra. So now you have 3 bases, and then I have to tell you why we have to consider not just Bangle's bases, but these other 2 bases. But anyways, you get bang, bracelet, band as bases of the quantum skein algebra. So I didn't prove that they actually form a basis. I'm just telling you that they do form a basis. And so now I have to tell you which one is better or which one is the best. And certainly Bangle's is not the best. That's why I'm considering the other 2. So which one is good? So at least I will tell you one property that makes one better than the other. And in general, these are bases, but we want to deal with algebra. So it's not enough to just have bases at our hand to describe what the algebra is. You have to tell us how to recover the algebra structure out of these bases. That is to say, you should know how to multiply 2 bases. So if you have a vector space's basis of a general algebra, B of an algebra, let's say curly A, what you do is you take the product of 2 basis vectors. And since this is also an element of the algebra, you can write it as a linear sum of the other basis vectors with some coefficients. And these coefficients are called structure constants of this basis. And these constants will live in the base coefficient ring of your algebra, whatever that was. And one of a very nice basis is such that, so in general, this is just living in the coefficient ring, whatever that it was. Sometimes these structure constants are all positive integers, so it's a very rare occurrence. And in that case, people say that basis is a positive basis. This is a positive basis if the structure constants are all positive. Well, in our case, the coefficient ring is not integers, but they're Laurent polynomials in A. So for us, positive means that it lives in every coefficient is a Laurent polynomial in A with positive integer coefficients. And I think I'm like done, so I have to tell you some result about this notion. So I have 3 minutes. So the first result known about this direction was by Dylan Thurston in 2014 that he proved Thurston 2014 that bracelet basis is positive. It's a positive basis of the classical skein algebra at 1. He sort of proved it by hand. And it's not completely clear how to prove the positivity, because if you multiply 2 pictures and then try to resolve the skeins, crossings by skein relations, then sometimes you get the unknot component, and unknot component gives you -2. So you have to control this minus, and he did control all the minus, and said that for bracelets, not bangles, bracelets, the resulting structure constants are all positive integers. And then he conjectured whether this is true for quantum. Conjectured either bracelets or maybe bands. Are they positive bases for the quantum? And his method doesn't work for quantum. And by now, there are some results about this conjecture, none of them by hand. Very, very heavy machinery. But I was just going to tell you that, but how on earth do you expect such a thing that, in general, in algebra, it's not sensible to expect that there exists such a basis. And I think if you just start from the definition of the skein algebra, there's no way why to expect such a thing happens. So there is actually a background story, which I don't have any time to tell you about. But the background story is, I'm just going to give you the name of that theory, is the theory of cluster algebras, or cluster varieties, or maybe quantum. And there is a special class of examples of cluster algebras which is closely related to the skein algebra. And there's a prominent conjecture in the theory of cluster algebras that there exists a nice basis that has positive structure constants, and that's why people sort of expected that same thing should be true for skein algebras. And he was able to prove the classical case, but the quantum case is like much, much harder. So at least I can say now a known theorem that bracelet for quantum and also bands are known to be positive. and for the quantum case. And as I said, none of these are by hand. And they use very, very heavy machinery called categorification, which I can't really say much about now. And I guess my time is up, so I'll have to stop here. Thank you.